Great. Thank you for having me and inviting me. I love this workshop, and I learn a ton every time I come. And today I'm going to be talking about some work in graphical modeling, talking mostly about inference, but towards the end we'll talk about learning, which is relevant for many people here as well. So I'll be talking about graphical models and the Bethe approximation. This is joint work with my students. So I'm interested in networks, large graphs like social networks or power networks or financial networks where you've got a lot of nodes interacting with edges. And one way to view these graphs is as a graphical model or a Markov random field. And really what a graphical model is a marriage of graph theory with probability theory. And what we like to do in my group is to look at these big graphs and view them as big probability distributions. And so there might be n nodes in this network. I like to think of, in a social network, you might have binary nodes saying if someone will buy a product, yes or no, or click on an ad, yes or no. You could think of a big probability distribution over all n users as n binary variables. But in the general case, these types of distributions are intractably large to store and to do computations with and to do learning with. And so exact algorithms very quickly become really inefficient. So a graphical model, again, is just a way of writing a probability distribution with a graph to make things a little more efficient. What we typically do is we write these things called bipartite factor graphs, where we have some variables, x1 to xn, which are round circles in the picture. And then we have square factor vertices, these little squares, which basically say that these two variables will interact together because they're both touching a common factor or function that ties them together. These two variables interact. These three variables interact with a three-way function. These three variables interact with a three-way function. And what this tells us is this big probability distribution breaks up as an exponentiated sum of these little functions. Or you can think of it as a product if you look at the exponentiated versions this way. And so this big distribution over 6 variables factorizes as a product of a little two-dimensional function times a two-dimensional function times a three-dimensional function times a three-dimensional function in this picture. And if these are all binary random variables, then these tables are the functions are just tables of size 2 by 2, 2 by 2, 2 cubed, 2 cubed. And so that's much less storage than the original probability distribution. So we've gone from 2 to the 6th down to about, let's say, 8, 16, 24 or so variables on the right-hand side. So we get efficient storage now of big probability distributions by doing graphical models. And of course, the savings are much bigger. If we think of a distribution over all Facebook users, there's about 1 billion users. If they each have a binary variable, that distribution is of size 2 to the power of 1 billion. But if we had a graphical model representation, we might work down to a size of maybe 4 times 1 billion if everything was just pairwise connected. So it's much smaller to represent that probability distribution as a product of a billion 2 by 2 tables rather than 2 to the power of 1 billion. OK, so we have storage efficiency. But unfortunately, we're not completely home free. We don't have computational efficiency. So it turns out the 2 key quantities or computations I want to solve with these graphical models are to do marginal inference or to compute the maximum a posteriori estimate in this graphical model. So marginal inference says, take this big distribution and compute just the marginal over one of the variables. So tell me the probability of, let's say, Cheyenne accepting or rejecting an ad or a product. Okay, so just give me that little 2-by-1 probability table. That involves summing over all the other variables. So that's 2 to the power of 1 billion work if you're looking at Facebook. Another problem is computing the most likely configuration. So tell me, what is, let's say, Tony's configuration in this massive social network, xi star, which is the highest scoring configuration for Tony. After I find the highest configuration that scores the best across all of Facebook, just tell me Tony's going to accept that product, yes or no, or that coupon, yes or no. And that also involves basically brute force search over 2 to the power of 1 billion different configurations. So these two things are not going to be doable brute force. And it turns out there's some bad news. They're both NP-hard, these two operations. And in fact, even more bad news is they're NP-hard to approximate to within epsilon. So if you said, OK, just give me something that's not the best configuration, but the second best, or epsilon away from best, that's going to take you potentially exponential amounts of time. And also, if you told me, give me the marginals plus or minus 5%. Don't give me the exact probability that Cheyenne will accept this product. Give it to me plus or minus 5%. That also could be NP hard and take intractable amounts of time. One little good news is map. This problem is sometimes easier to solve than this problem. So some graphical models you can do map with, maximum a posteriori, but you can't do marginal inference with that. So this one remains P, whereas this becomes NP hard. Good news is, at least if the graphical models are acyclic, these problems are easy. So if you're dealing with a tree-structured graphical model, both of these problems can be solved in polynomial time or actually linear time. So that's great. Unfortunately, most models we really care about, things like social networks or medical diagnostics networks over symptoms and diseases, all these really juicy, interesting problems are not acyclic. So here's the algorithm people use for acyclic models. This was devised by Pearl and others in the 1990s. It's basically a message passing algorithm commonly called belief propagation. What we do is we send little messages called sum product messages from the round nodes to the square factors. And these look like little products of tables. And then we send messages from the factors to the variables, which look like a sum of a bunch of products as well of other tables multiplied by the factor functions exponentiated here. And if you iterate these messages, don't worry about the exact form. These are just little sums and products. Eventually, your messages will converge, and then you can compute the marginal over the variables you care about just by taking this little formula of a product of incoming messages times an exponentiated factor. So this is a very simple update rule, and it gives you the marginals if you have a tree-structured graphical model. If you replace this summation operator with a max operator, then you get the map solution you wanted. So you can get marginals and map really nicely for trees. If you don't have a trees, what you can do is you can still use this algorithm, but you have to convert your graphical model into a tree. And this requires a step called triangulation, which turns your graphical model into something called a junction tree. But this typically enlarges the cliques in your graphical model. And the propagation rules we just saw are actually exponential work in the clique size. So if you make big cliques, those little cute messages we were sending around become really painful to send around and very slow. And so here's an example of triangulation. I've got this graphical model. It's got cycles. We can add extra factors, hallucinate these dependencies that don't actually exist, and then we form these triplet dependencies now. But now this is a tree or a chain, actually, and we can do the previous algorithm and it will converge, whereas it might not converge here if we ran the previous algorithm on this loopy model. But the cost is we've gone from these little, let's say, pairwise functions to these triplet functions. And so little 2x2 matrices have turned into cubes, and things are slowing down. And so this really shows kind of the limit of these junction tree approaches. The tree width of your graphical model is going to be the dominating factor, and your exact inference algorithm is going to be exponential in the tree width. And unfortunately, for many real graphical models, like social networks, like Facebook or power networks, the tree width is really big. So you can't use this approach. So instead, people said, well, how about we just skip this triangulation step? Let me just forget about triangulating and just run the messages around in loops. And so this is called loopy belief propagation. And you'd run the sum product algorithm to do marginal inference. You run the max product algorithm to do map inference. But because it's loopy, we can't really prove too many things about it. Today, I'm going to be focusing on what this loopy belief propagation algorithm is doing. But one caveat is that the graphs are not acyclic, so they're not trees. It may diverge, or if it converges, it can converge to really bad local optima and doesn't find the global optima we want. OK, so let's look at a couple of graphical models specifically. So these are what we call attractive graphical models or supermodular models. In this picture, I've drawn only red edges, because each edge, when it's red, I mean it's an attractive edge. And so what this means is the factor, or the potential function tying these two variables together, satisfies the following property. The factor has, if it's just a binary table, the 0, 0 entry and the 1, 1 entry have a higher value than the 0, 1 and the 1, 0 entry. So this is called attractive because this binary node and this binary node get a higher score from that factor if they agree. If they're both 0 or they're both 1, you get a higher score. If they disagree, then you get less a lower score. And so that's what this inequality really says. So this is like a supermodular relationship between these two variables. OK, so these models are actually used very often in things like image smoothing. If I have an image of some X-ray with some artifacts and I want to find the veins here, instead of just thresholding, I can run something called graph cuts and find the map solution of this graphical model, which is fully attractive, which basically says I've got these potentials that encourage pixels to be bright if their neighbors are bright and dark if their neighbors are dark. We don't like when you disagree with your neighbor and you're dark and your neighbor's bright or vice versa. So this is the probability distribution. It looks like what we just saw before. It's a grid graph. And we can find the most likely configuration efficiently with graph cuts. This has been known since a couple of decades now. Unfortunately, computing marginals is still hard for this problem. OK, so that's for attractive models, things like image denoising. But more generally, we don't have just attractive supermodular edges in our graphical models. We also have repulsive edges or submodular edges. So in this picture, I've drawn solid red edges to be attractive edges and dashed edges to mean repulsive edges. So remember, attractive meant you get a higher score if you agree with your neighbor. You beat the 0, 1, and 1, 0 configuration. Repulsive means you get a lower score if you agree with your neighbor. OK? And so dashed edges are repulsive. And so these types of models have been known for a while. Harari in the 1950s started to work with these sign models. He also defined this idea of a frustrated cycle. So if you look at these, think of this as a social network. We've got 6 professors here. And red edges means the professors are friends. And blue edges, or dashed blue edges, means they're sworn enemies. And we're trying to decide who's going to go to the banquet tonight. So we're going to see that, for example, a frustrated cycle exists because it contains an odd number of repulsive edges. So here's a frustrated cycle, x3, x5, x4. That's got 1 repulsive edge, which is an odd number. And so that's a frustrated cycle. And so the reason this is frustrated is because if you did kind of a local message passing algorithm like belief propagation, it's never going to settle down. And we can just see that very intuitively here. Let's say Professor X5 wants to go to the banquet. X4 notices Professor 5 is going to the banquet, and they're friends, so he also decides to go to the banquet. Then X3 is enemies with X4. He says, oh, Professor 4 is going to the banquet. I will not go to the banquet. I refuse. So then he doesn't go to the banquet. But then X5 notices, oh, his friend X3 is not going to the banquet. So he goes, I'm not going to go to the banquet. I changed my mind. And so then you get this oscillation behavior. So frustrated cycles prevent these types of message passing algorithms from converging. This is kind of an intuitive explanation. It's not kind of a formal theorem. That's kind of where you get these frustrated effects. And these typically cause issues with convergence. And so Muij and Kaplan in 2007 studied the convergence of some products in both fully attractive settings and in the signed settings. And what they noticed is as you go from repulsive to attractive, the algorithm seems to converge more and more. So white means the algorithm is converging. Gray means the algorithm is diverging. If you have very low attraction and very low repulsion, you're in here, and the algorithm will always converge. But when you have very strongly attracted pairs, you can start getting divergence. And if you have very strongly repulsive pairs, you more often get divergence, actually. And this is kind of how strong the singleton potentials are, encouraging you to be 0 or 1. And this is the level of repulsion. This is the level of attraction in a model. So as you get more repulsion, the algorithm doesn't work. And even if you have attraction, the algorithm doesn't always converge either, this belief propagation algorithm. So we're trying to fix this problem, which is kind of loopy belief propagation is not working half the time. And so we said, let's study this a little bit more closely. It turns out loopy belief propagation is a heuristic for minimizing this quantity called the Bethe free energy. People knew that in 2001. Let's try to revisit this Bethe free energy and try to do better. So we're going to try to find an algorithm that computes this little marginal out of this big distribution efficiently, not by doing this brute force sum. We're going to try to find a polynomial time algorithm. And what we're going to do is try to do a better job of minimizing this Bethe free energy than what loopy belief propagation does. We're going to try to find a polynomial algorithm rather than loopy belief propagation, because it gets stuck in local optima and stationary points that are suboptimal. OK, so here's the approach. Marginal inference is just the summation of this big distribution over all variables except x. And the distribution, we said, looked like this x of a bunch of factors. It turns out this is exactly equivalent to computing just the normalizer z. You can view p of xi as just a ratio of two different z's. So if you can compute z, you can compute pxi. So the name of the game is computing z efficiently. All right? And it's been known for about a century that log z is equal to the minimum of the free energy, the Gibbs free energy, which is find a distribution that has high score. These are the scores inside this x. So a distribution under which, when I take the expectation, I get a high score, plus has high entropy. I want to find a distribution Q with high entropy that kind of aligns with my scores. If I can find that distribution, then I can compute this log z. Of course, this problem is not easier than this one. They're both equal, so there is no trick here, because you solve for a distribution over Q here, which is a distribution over n variables. That's just as hard as summing over all the n variables. So we haven't gained anything. Just this is kind of a mathematical equivalence without any computational gain. So in 1935, Hans Bethe proposed an approximation to this Gibbs free energy, which was later called the Bethe free energy. In many ways, Hans Bethe is considered one of the grandfathers of statistical physics. He's contributed a lot to statistical physics. He won a Nobel Prize for discovering fusion. Really brilliant physicist overall. But in 1935, he said, let's avoid this Gibbs free energy and work with this version, which is simpler. So instead of saying log z equals this optimization of the Gibbs free energy, let's replace the entropy S. Instead of computing the entropy of Q, let's compute the sum of the pairwise entropies of pairwise marginals of Q. So approximate the big entropy of Q by an average over all its pairwise little 2x2 marginals. Okay, so that's this kind of pairwise entropy. And in addition, instead of finding the best distribution Q that lives inside the space of all possible distributions, relax the space from the space M of all possible valid distributions to the space of all positive functions that are pairwise consistent. So pairwise consistency is a weaker condition than being a valid distribution. I'm just going to find 2x2 tables that represent Q that sum and have consistency so that, let's say, Q of x1, x2, when I sum out over x1, is equal to Q of x2, x3 when I sum out over x3. Okay, this is kind of pairwise consistency. It's a weaker condition, so it's a relaxation. OK, so what we're going to do is we're going to solve this Bethe free energy computationally. We're going to try to find a Q that minimizes F. And it turns out what matters is to find Qi scalars, which represent the probability that xi is equal to 1. And 1 minus qi is the probability of it being 0. And then we're going to find little 2x2 tables for all pairs of variables that are connected in our graphical model, which are the pairwise probabilities of xi and xj being 0, 0, 0, 1, 1, 0, 1, 1, 1. So whenever there's edges, I need to recover a table like this. And for every node, I need to recover a scalar like this. Turns out we can rewrite this table this way as a function of these two scalars of qi and qj and some other single scalar variable called xi And it turns out we can minimize over xi ij analytically. This was known since 2001. So it turns out all I really need to optimize is over n scalar values, q1 to qn. That recovers my q function. Of course, this is still a hard problem because I'm solving this optimization problem over n scalars. And loopy belief propagation is trying to do this in a greedy way and getting stuck. So we said, let's try to find an algorithm that's global, that doesn't get stuck. So loopy belief propagation slides around and tries to find a pretty low energy configuration of these q1 to qn scalars. Instead, what we said is, let's try to find the optimal solution. And the way we'll do this is we'll create a mesh. So I've got q1, q2, and q3. Instead of doing a local algorithm, which I initialize randomly and I let it slide downhill, I'll discretize my space. I'll chop up q3 into 11 different buckets, q2 into 3 different buckets, q1 into 6 different buckets, and try to find a discrete solution that's the minimum of this Bethe-free energy. And I want to find a discrete solution when I minimize that's no worse than the optimal continuous minimization plus epsilon. This is going to give, so if I'm walking on the grid, I'm never going to be as good as minimizing continuously. But I want to make sure that I'm not too far off, that when I find a solution on the grid, I'm epsilon away from the optimal. And so this is a picture of what the energy looks like. We have to figure out how to discretize along Q1 and Q2 and all these different Qs so that I can find this solution on the grid. It's not too far from the global optimum, but it's still better than this local optimum. And if I discretize finely enough, I'll catch it with an epsilon. And so if we discretize an attractive model, it turns out I can find the minimum of the discretized problem in order sum of all the different discretizations, all cubed, okay, through a graph cuts algorithm. So I want to avoid over-discretizing, obviously. If I discretize too much, this is going to blow up on me. Turns out if you only discretize 0 and 1, you're solving the original map problem. Again, with the exact same graph cuts code that was used for the X-ray problem. So we looked at two possible ways to discretize. We looked at discretizing when the function has high curvature, discretize more quickly. When it has low curvature, you discretize less quickly. This makes sense. High curvature functions, you've got to discretize quickly to catch the minimum. And this led us to a polynomial time algorithm for minimizing the Bethe-free energy. If you bound the gradients, so functions with high gradients have to be discretized very quickly. Functions with low gradients, you can kind of discretize less quickly because it's not changing too much. Then you can achieve a nicer polynomial algorithm, which is kind of cubic in the number of variables and the number of edges. And both of these algorithms find an epsilon close solution for Z beta. So this is global optimization of a non-convex function, when before people were doing kind of loopy belief propagation and getting stuck at fixed points and stationary points. And so here are some runtime experiments. It scales much better to do gradient-based discretization versus curvature-based discretization. And here's an application. We looked at some transformers in New York City. We have a big network of transformers. They each have a binary variable saying, is a transformer going to fail next summer, or is it going to work next summer? And we want to compute from this big distribution the probability of failure for all the transformers. And if we have a singleton probability of failure, and we have a coupling, because transformers that are neighbors to each other are going to fail in similar ways. They're going to send surges along the same cables. So your neighbors fail, encourages you to fail, or if you succeed, your neighbors will succeed. So we have a bunch of attractive edges between these transformers. And we ran our algorithm just to compute P of xi for each transformer, and then use P of xi to rank order the transformers to say these have to be repaired more aggressively than these before they fail next summer. And that gave a better AUC than independent ranking when we just use the singleton potentials by themselves instead of coupling things with the network. We also looked at non-attractive models, so these signed models, and said let's compute marginals also for these models. So here we have e-pinions. So instead of just having attractive edges, some users and e-pinions are friends, and some users are sworn enemies. So you can download this network and say, OK, red edges means these guys are friends, blue edges are enemies. We'd like to use these types of algorithms that we just described before, but it turns out for signed models, you can't get a polynomial time algorithm. Remember, signed models have both attractive edges and repulsive edges, where you get a higher score when you agree for attractive, you get a lower score when you disagree, you get a lower score when you agree for repulsive. So we want to apply the polynomial time algorithm we just saw to e-pinions and compute for each user the probability they'll be trusted or suspicious. And we again have these potential functions that tie them together. So a guy with a lot of enemies should be more suspicious than a guy with a lot of friends. So we couldn't run the algorithm out of the box, but we found this nice little trick to convert any signed graphical model into a purely attractive model. And we published this last year in NIPS. We said the title was called How to Make Graphical Models Attractive. Okay, so you take your model. It's got some blue edges and some red edges, supermodular and submodular edges, and you create a clone of your model. You keep the red edges in the original, and you keep the red edges in the clone. But they lose the blue edges, the repulsive edges. And then the formula is to connect each node in the original, which had a, so if node I and node J had a repulsive edge in the original, you connect node I to its clone, to clone J, and you connect clone I to original J. And so you get repulsive edges between these two copies. This is called a double cover construction. Yeah. So we do have frustrated cycles in here, but the key is this is going to be only red edges here and only red edges here and blue edges between them in the double cover construction. So this effectively says you only get repulsion between nodes and their clones, but not internally between the originals and internally between the clones. And then what we do is we flipped the nodes on one side and redefine 0 to be 1 and 1 to be 0 on one side. So when you flip the definition of 0 and 1 in this partition, this cover over here, the red edges stay red because attraction remains. I become 0, if my 0 becomes 1 and my neighbor's 0 becomes 1, we still stay attracted to each other's configurations after this flipping. However, all the blue edges now become red. Everything becomes fully attractive now once I do this flip. So this makes a fully attractive graphical model out of the original graphical model. And so then we do inference on this guy. We compute our partition functions and our marginals on the right-hand side. OK, so this is a different graphical model I just created. How is this related to what I cared about initially? Well, we proved last NIPS that the partition function you compute in the double cover is an upper bound on the original partition function. So we're basically able to solve for an upper bound by doing this trick, but now it's a fully attractive model where we can run a polynomial time algorithm, and we can, for example, now start computing the trustworthiness of all these different users in this piece of opinions where I've shaded them by how trustworthy they are by running the original polynomial time algorithm on the double cover. Another interesting property is this double cover construction seems to always get really nice behavior with loopy belief propagation. So we only have empirical evidence for this. But if you run belief propagation on opinions or on grid graphs or on deep networks, like deep belief networks, it very often doesn't converge or converges to suboptimal solutions. But if you run belief propagation, loopy belief propagation on our double cover that we just constructed, for some crazy reason, I don't know why, it always converges. And it converges very, very quickly. You can see the number of iterations and so on. And other types of modifications of belief propagation, like tree-related belief propagation and all these other schemes, also have trouble converging and take lots of iterations. But for some reason, when you create this double cover, you make it fully attractive, and it's nice and symmetric. It looks the same on both sides. This creates a better convergence behavior for loopy belief propagation. So you don't even need to use our polynomial time algorithm when you have a double cover. OK, so very quickly, how is this all related to learning? Well, we just talked about marginal inference. Turns out to do learning, let's say I have a bunch of xy pairs, and I'm trying to learn a conditional model, P of y given x, from a bunch of xy pairs. We typically do that by maximizing log likelihood. So here's the log likelihood of my xy pairs under this model, this parametric model. I'm trying to recover theta. And we often regularize the theta, like a quadratic penalty. OK, so how do we do learning in conditional random fields or for logistic regression or all sorts of things like that? We take derivatives of the likelihood, and we do gradient ascent. So here's the gradient of this log likelihood. Unfortunately, if the graphical model we're trying to learn is one of these high tree width graphical models, it's NP hard to compute its partition function or to do marginal inference. And we need marginal inference over here to be able to compute our gradients. So to do learning, you have to do marginal inference. And so typically what people do is, for hard models and retractable models, is they do an inner loop. For each gradient step, you run loopy belief propagation until convergence. You get your gradients. You take a little step along the gradient. Then loopy belief propagation again. So you do this double looping algorithm. The outer loop's gradients. The inner loop is loopy belief propagation. And that's a really hard thing to get to converge. It becomes a real nightmare. So what we said is, let's just not look at loopy belief propagation. Let's go back to the Bethe approximation and apply it up front. So replace all the log z's with log zb's, like we just did before, and rewrite your likelihood. Instead of the original likelihood, maximize the Betha likelihood. We'll replace all the z's with log zb's, which basically involve a minimization over some distribution q. So we've got this max over theta, and inside each term, I've got a min over q. So OK, I'll just wrap up very, very quickly. So this is a concave maximization, convex minimization. You can apply psion to flip the mins outside of the max. And it turns out then you can get the theta analytically. This is just a quadratic optimization over theta. So we get theta analytically, and all we're left with at the end is just a bunch of minimizations over the q's. And this can be done with Frank-Wolf. The q's are probability distributions that have to sum to 1 and be pairwise consistent. So this gives us a convex hull of constraints. This is a nice convex function. So we do Frank-Wolf. And what's really beautiful is each step of Frank-Wolf is just map estimation, the very first problem I was talking about. And very often, that map estimation problem is much easier than marginal inference. So by doing iterative map, we can do learning instead of doing iterative marginal inference. And it's much faster. So we've tried this. This is the algorithm that I just described. It's guaranteed to converge at order 1 over t. We've done this for matching images, for image segmentation, for matching roommates in dorms. And it's faster and more accurate than kind of SVM variants that try to do these problems without graphical models and kind of do structure prediction instead. And we're also using this to learn graphical models of financial data and news feeds. We're using a technique by Wainwright, Ravikumar, and Lafferty to learn the graphical model structure. I'm going to skip this very quickly. But once we've learned the structure, we then maximize likelihood, and we can start fitting graphical models with structure and parameter learning to these large data sets that we're getting from Bloomberg, these financial data sets. And we're getting better than naive graphical models and tree-structured graphical models. And here's an example of parts of a graphical model we recovered that show how energy stocks are kind of interacting nicely over here. And we have other stocks that are sometimes attractive, sometimes repulsive with each other. So we can learn these graphical models from data sets. And they're much more intuitive than these Chow-Lu tree-structured models. And we're also learning this now from neuroscience imaging data sets, where we're getting firing patterns from this hydra. It's a see-through kind of organism. We can see the neurons firing. We get neuron firing chains, and we learn graphical models of these things as well with structure estimation and parameter estimation, and then inference using kind of the Betha techniques I just described. So just again, to summarize, our goal is to perform inference and learning with large networks and to deal with these big distributions, px1 to xn. But all the computation is intractable if we want to do it exactly. So instead, we do Betha marginals and Betha learning. And things seem to be working and scaling well, especially with this Frank-Wolf learning algorithm. And I'm hiring 3 postdocs that will hopefully explore machine learning for finance, neuroscience, and climate. So if any of this stuff's interesting to you, please come talk to me about these postdoc opportunities. Thank you.